nested if-else conditions can be really tedious really fast. For example, take a look at this function. It is trying to classify penguins based on the body mass, species and sex, and it uses a whole bunch of conditions inside of this function to figure out if a penguin is underweight, overweight, or just normal weight, or whether there is even some missing data. And this function is really convoluted, and in today's video I want to show you how to avoid such a mess. And once we're done with that, we're also going to look at a couple of different techniques that you can use to avoid writing this sort of code in the first place. So with that said, let's dive in. Now, before we dive into our code, let me mention that this video is inspired by ARIAN-CODES. It's a super great channel here on YouTube that shows you how to do a whole bunch of code stuff with Python. I really enjoy this channel, and a very similar video about how to avoid nested if-else conditions was released on ARIAN's channels recently, and I figured I want to do something similar with R as well. So with that said, make sure to check out ARIAN's channel if you're also interested in Python. Now, coming back to our function here, let's take a look at what our classify penguin function actually does. So let's load the stuff here, and then let's have a look at our data set that we want to use. Naturally, it's a data set about penguins. It's our favorite Parma penguins data set. And then we can select the columns we need. And then we can use the pmap function to iterate over each row to get the classification for each penguin. And if we want to figure out, okay, how many penguins are there, then we see that with the table function, we can figure out there are 7 missings, 204 normal penguins, and so on. So that's really what we're going for here. And our function iterates through a whole bunch of if-else conditions to get this job done. But of course, this is messy, so let's do better. So let's duplicate this function here, and let's call this classify penguin new. So with that, we have a new function and the old function, and we can always go back and forth and see how to make things better. And more importantly, we can take the old function, run some code, and take the new function and run some code and check if these things match. That's important when you refactor a code like this, because you kind of want to avoid destroying the logic of your code. And the way to do that is to implement tests. So let's start with that first. What we can do here is to take a function from the test_that package, which also has a function called test_that, and then we need a description, and we write something like penguins are classified correctly. So here the idea is that this test_that and this description is supposed to form a sentence. So here we want to test that penguins are classified correctly. And in there we can put in code that tests these things, and test_that also has a whole bunch of expect functions. And here we want to make sure that the things that we get later on will be the same thing as we currently get when we run the classification. So we can say the object that we currently have, that's this data frame here, is supposed to be the exact same thing as we get here. So naturally, if I run this code, hooray, my test passes because the object and the expected object are kind of the same thing. And now, instead of using classify penguin, we're going to use classify penguin new here. And then if we run this, we see that, okay, this test failed because I haven't actually sourced this function here now. And now I do have a mechanism to check if all of my code still works. And now with this setup, we don't need this part here anymore. And now we can work on our new function here. The first thing that we want to do is to move from the outer conditions into the inner conditions and remove the else part at every step of the way. And here we can do so by first looking at this else conditions, because it's the outermost else condition inside of this function here, because this is the if part. And now here comes the else part. And my go-to strategy is to always remove the else part and only use if in mostly 99% of all my use cases. So what we can do here is to refactor these conditions into variables. So let's take this first if condition. Let's take this part here and wrap this into a variable called has low body weight. This means it doesn't have a missing body weight and it is less than 4,000. And now we can use this stuff in here. And now we see that here's another condition. Let's write this as has a missing property. So let's do has missing property and let's throw in this code in there. And then we can use this part over here. So really we have done nothing different. We've just shifted things around a little bit. And now comes the actual refactoring of the first if condition or of the first else part. So what we do here now is to say, okay, in order to return this missing thing, we need to not have a low body weight and have a missing property. So if not has low body weight and has missing property, let's return this missing stuff here. So let's take this part here and then we can create another if condition and say, okay, now if not has low body weight, this is the other stuff that is in here, let's return normal. Okay, let's do that. So now we can remove this part here because if this thing is reached, then it means that these if statements must have been jumped. So that's how you can always get rid of the else part by simply taking the thing that you want to put into the else and putting the opposite into an if condition that comes before that. It's kind of a safeguard before you run into the actual code that you want to run. So here we simply have a first few checks, and if these don't work out, we throw the normal or missing thing back, or if these first checks work out, then we can go into the other part of the logic. So let's save this and let's rerun this, and we see that, hooray, our tests still pass. And actually I forgot one important part here. This if statement here now is kind of redundant because if we reach this, it is clear that this thing is true. So we can simply remove the outermost if condition and everything still works the same. And the key here why this works is because we have all of these return statements inside of this if conditions. That's a key thing to remember here. So now let's worry about the species. We can see in our function that the next step of if else conditions really always just checks what species is the penguin. So what we can do here is to rat this out into different species here as well, or into different if conditions here as well. Let's get rid of this else statement. Let's get rid of this else statement. And then if we rerun our code, everything still works the same. But the nice thing now is that we don't have to worry about this if else thing if we read this code. Instead, we can just check, okay, no, this isn't true. Let's move there, or let's move along. And in this case, I'd also sort it so that the easier conditions happen first. So now with these easy changes, let's talk about something a little bit more involved. We can see here that multiple paths through our conditions lead to the same value. For example, we can see here that if not has low body weight, we get normal. If species is chin strap, then we also get normal, and so on. And the same thing happens for underweight. We see that we return it in these instances, and for overweight, the same thing happens as well. So what we can do is to collect these kind of conditions that lead to, say, normal being returned into a vector, and then simply check if one of these conditions is true, and then return the thing accordingly. To do so, let me just copy and paste this part here so that we have multiple instances of our function here, so that we can later on also run a little benchmark on this to see if our code might be slower now. But of course, the goal here is that we become faster, not slower. Let's see how that works out. In any case, we can see here that these two things return normal. So we can just say, okay, the normal conditions are these two things. So not as low body weight and species is chin strap. And now what we can do here is to remove this part and remove that part, and instead check if any of the normal conditions are true. And now we can run our tests again, but we haven't used this new function here. So let's put in, instead of classify penguin new, let's put in this new function here. I'm really using terrible naming here, really boring new 2, new 1, and so on. But for this little dummy example, it works fine to use these silly names. If you write production code, make sure to try to use reasonable names. In any case, now we see that things still work. The data frames that we get at the end still look the same. This means that now we can do the exact same thing in these conditions here. In this case, let's collect conditions for penguin being underweight. So let's do underweight conditions. This will be a vector again. And now we have to collect all of the conditions here. So the first condition is that the species is ATHLY, and we have that this thing here is also true. And then we can do this same thing here. Let's take this part and we want to have this part. These are our conditions for something being underweight, or not something, a penguin being underweight. By the way, all of these conditions here, they probably don't make much sense. I've just made something up as a dummy example. Don't think these are real good classifications for penguin weights. But this silly example works fine to demonstrate that now we can do the same thing as before. We can use the any function to check if any of the conditions here are true. And if so, we return underweight like we wanted to. And the nice thing is that in the other else statements here, we just return overweight. So what we can do here is to say in the last step, return overweight. And if we remove this part here now and check, we see that, hooray, our tests still pass and our code got so much shorter. We now have a bunch of normal conditions. So we see that in these cases, we return normal. Then we have a bunch of underweight conditions. And we see that if one of those is met, we return underweight. And then here we have some other checks that helps us to return missing. So from this, it becomes easier to read the code. We don't have to jump deep into nested if-else conditions here. So that's nice, but our function currently still has a crucial flaw. The original function had it as well, but now we're kind of so close to a better version of this function that we can also improve the original design. You see, inside of this classify penguin function, we always have to iterate over all of our rows inside of our data set. So we can't just take these full vectors out of our data set and stick this into classify penguin. No, instead we have this pmap function that iterates over each row separately so that we always only stick into this function one number, one species, and one sex specification. And there are two reasons for why this needs to happen. The one reason is that these double and double or conditions, these things only work nicely with a single booleans or single conditions. For example, if I were to use a vector, say true, and then do and false and true here, then I'd get an error that says, okay, this double and, it doesn't work with things of length longer than 1. So instead I have to use a single and. In this case, it just does component-wise and operations, checking true and false will give you false, true and true will give you true, and so on. But that's the idea here of having to use a different AND operator. And the reason why we've used this AND operator here is because it is usually faster. Because if this thing is already false, there is no point in checking what comes after this. And you can see this really easily if you just try to take a false and then say and then you put in something that cannot be even compiled, and you run this and you still get a valid result. That's because R doesn't even try to touch anything that comes after this because it is already false, it has already found a false, and this double and simply then says, okay, I already got my answer, no need to check anything else. But with this single and, we'll see that, okay, there is a problem, this thing here isn't defined. So these are the subtleties here between the operators, and if we want to make this function into something that can actually work with vectors in these arguments instead of just single values, then we need to change the operator. That's the one thing I mentioned that we need to change, but also even if we have the single and the single or everywhere, we will still have it inside of this if statement. And this if statement can really only work with one condition. For example, if I say if and then put in true, false in here and say print 1 and I run this, we see that, okay, the condition has length larger than 1. And that's because the if function or the if statement also expects a single thing, a single true or false in there. So this is why this function simply doesn't work with vectors like we want. And in order to make this possible, let's copy this part here into a third function. Let's do function number 3, and then let's set up our testing function to also use that. And now if we run this, we still see that our test passed because we haven't done anything different yet. And before I show you the cool strategy that we can apply here to use vectorized calculations and make things faster, let me mention that If you like this video, and I'm hoping no one is in the else part of this condition, if you like this video, make sure to give it a thumbs up so that I know that you enjoy this content, and also the YouTube algorithm knows that you like it and spreads the word to other people watching YouTube so that more people can enjoy this R content. It would really help me out a lot, so thank you for that. And now let's get back to the content. So the first thing that we want to do here is to remove all of these doubled operators, just so that we can work with vectors. So here we'll need that, here we'll also need that, here as well. I'm pretty sure I will forget something, but for now, let's just try. Okay, so this was step number 1, making all of these double logical operators into single logical operators. Now let's worry about these if parts here. What we can do, instead of having all of these if statements in between, we can have a single if-else function at the end of our function. And then we now list the conditions we need. So we start out with this condition here. This is a vector. If we put in a vector of things into these arguments here, this will also be a vector of trues and falses. So let's stick this in here. And actually, since we want to have multiple different options, we don't use if else, but instead we use case when. And in this syntax, we then say, okay, in this case, return missing. So we can remove this part now. Then we can do any normal conditions and return normal. In case you're wondering, will this work the way we're doing right now? And you already see the flow of what I do, be sure I will show you that it doesn't exactly give us the result we want to have yet, but it isn't hard to tweak it to get the correct result. So stay tuned is kind of the message I want to say here. So with that, we can get rid of this part here. And then let's also take these underweight conditions and say in that case, we want to return underweight. And then if we've used all of our conditions, we wanted to return overweight. So let's make that the default and say, if you can't find any of the other conditions before, return overweight. So with that, we can save this, and we see now that our function already got much shorter because we don't have these if-else blocks anymore. Instead, we have it all comprised into this vectorized version of if-else, and in this particular case of case when, which can take not only one condition and then say do this one thing or the other thing, so not a true if-else, but more if-else, else-if thing. So either way, we can now run our code, and this is currently still passing because we're now still running this operation one by one, because here we're iterating over all of these things. But what I want to do now is to simply take our new function and then from the penguins data set, stick in the body mass, and then we can stick in the species and the sex column, and then we can get rid of this part here. And now running these tests, we see that now, okay, now the tests failed. And currently it says unused argument because we have still a comma here, and we only want to have 3 arguments here, and with another comma it kind of expects a 4th argument. So now let's run it again, and now we see that our tests still fail. The beauty of having this set up is that we see that, okay, there are mismatches. There are 113 out of 344 mismatches. And this is a safety net that helps you that what you rewrite here is actually still conforming to what you wanted to have in the beginning. So here let's check what goes wrong. And really it is a subtle thing here. So let me just tell you what's going on here. If you stick in vectors into this, then this means that these things here are also going to be vectors. And this means what you want to have in these conditions vectors is not these 2 vectors that you had before, this and that, combined together into one large vector, but instead you want to keep them separate so that you later on can compare these conditions one by one. So this is why instead of using this C function that just combines everything into one vector, you have to use lists that keep the vectors in separate parts. You can see this, for example, if I tried C and then do true false here and do another true here, you'd see that this thing becomes one vector. But if I use a list, this thing becomes a list of the original vectors. And now I can compare this true with that true, and whether I use an and or an or, it will be true. And here I could also check false, and true would give us false. But since I want to check any of these conditions, I check this or that, and then I'd get it true. So this means we need to have these lists, and this is why I've made the changes here accordingly, so that these vectors here will stay separate from this, but they're all just collected inside of this list of vectors. Unfortunately, our any function doesn't play nicely with lists. For example, we can create a list of trues and falses here. So we have a list like that now. And if I try to run any on this list, we see that, okay, this doesn't work because any expects a vector. So what we wanted to do instead is to iterate through all of these things one by one. Basically, we want to go through this column-wise. But what's even better than going through this column-wise is to simply go through this vector-wise. So we first apply this and stick it together with this using the or operator. So for example, we could do L1 or L2. You see, each of those gives us a vector, and now we could iterate through all of this. And then we could also do L3, and then we'd combine all of these things. But having to hard code applying this or operator is kind of tedious, and that's why there is a helper function for this. Namely, there is the reduce function. It helps us to get this exact result by iteratively applying this or operation. And to do so, we can just stick in the list and say apply this operator. You have to put it into these backticks here and then iterate through all of these steps. So now if we try to execute this, we see that we get our final result back. And what reduce does is that it takes the first entry of our list, which is this vector, and then applies the operation together with this thing here. And once it has the result of that, it has a new vector and it will stick that together with this part here. You can see this by the familiar function or by the sister, brother, whatever, the sibling function of reduce, which is accumulate. It does exactly the same thing as reduce, but it keeps the intermediate steps. So what it does here is that it starts with 1, it starts with this thing here, then it will also check what is 2, it's that, and it will combine these things into 1. And now it will then take this new result and combine it with what is inside of 3 and will give you this result. So really, that's how you can combine these lists of trues and false vectors using the or operator. You'll have to use accumulate or rather reduce to get the job done. So let's do that here. Let's use reduce here. Let's use reduce there. And then let's do backtick or, and then let's do the same thing here. And now what we can do is to run this. And now we see that our tests pass again. So that's super cool. We now have shorter code and we also get the same results. And the nice thing here is that even if you don't know this reduce pattern yourself yet, you can still understand, if you think about it for a second, that okay, there are these things like normal conditions, there are these things underweight conditions, and here there's the operator or involved together with these conditions and you return normal. So even if you only know case when and know that this or operator is combined with a vector called or a list called normal conditions, you can figure out that okay, it will try to check whether one of these conditions is true, and if so, it will return normal. Same thing goes for the underweight conditions, then it will return underweight, and so on. So that's a neat little thing here. It's sort of readable even if you don't know the reduce pattern, and it is extendable quite well. If you have many more normal conditions and underweight conditions, you can simply make this list longer. So that's super helpful. Of course, what you could also do if you really don't want to use the reduce pattern, you could wrap this into these parentheses and then use the or operator manually. Have this here as well, and then you don't need the list here. And then you could use the normal conditions like a vector here as well. So if you do that, you still get the exact same results, and there's nothing wrong with that. But you can see if you want to have this part here, it might become, or it might start to get messy kind of fast. Because if I have to wrap this also in parentheses, then I have an extra set of parentheses here. Then I have to chain this together with this or operator. It's a question of design choice. You can either use this or that. But my point here is that now that you know of this reduced pattern, you really have the choice of choosing either one or the other. All right, cool. So now I promised you that we'll also compare these refactored functions in terms of their speed. For that, I can show you a little benchmark code that I've set up. Let me just copy this in here. It uses the micro benchmark package to micro benchmark different code chunks. So here, this is our original code. Then we have our original code, but with this new function. Then we have it here with the second refactor, then with the third refactor, and then using the third refactor, but in a vectorized fashion. So now if I run this code, it will try out all of these code chunks. It will run them 100 times, and it will measure how long each iteration takes. And then it will give me an overview for each name that I've specified inside of the micro benchmark function here. And what you can see here is that you get different statistics like mean, minimum, and maximum time, currently in microseconds, of how long this operation took. And you can see that our initial function did quite well. And the more we refactored, it actually got really worse. And especially when we were refactoring so that we can use vectorized functions, but then decided to not use vectorized calculations, but instead iterate one by one, and you see that it got really bad. But the good news here is that the moment you actually switch to vectorized calculations and then use this new function as intended, then you see that it gets much faster than our initial design. So that's a pretty cool bonus if you ask me. But of course, if time or speed isn't your concern, then you can also feel great just about the fact that this code is shorter now and easier to digest than this mess of a whole bunch of if-else columns or if-else statements. So now we've learned a couple of techniques to refactor this. And in fact, if you start writing your code from the beginning like so, then you of course don't have to refactor later on. But that's really how it happens. You start to write simple code and then people extend it over time and then it's a mess. So at some point you'll probably have to refactor, and you now seen a way to make that happen. And another way to do that is to use dictionaries to look up different options or functions that you need. And for that, I've brought you another function that we can use as an example, and it will be short, so don't worry about this video getting super long. Here I have a simple little function that does nothing but return a color. So if you source this function and then do get color, and you want to get the color for A, then you see that you get the color red returned. And it's a chain of these else if statements. That's not particularly nice, but that's what we currently have. And due to the fact that we're always using these if statements, we cannot use multiple categories to say get A or D, because then we run into this issue of having conditions of length larger than 1 again. So that's not nice, but you already now know a pattern that you can use, namely this case when thing that you can use to return all of the things that you want. So you could rewrite this with case when, and then you'd be done. But another way to make this happen involves storing the information of which category relates to which color, and then simply look that up from this list. So what you could do is to create a named vector like so. If you just execute this part, you see that you have a named vector with names A, B, and C and the corresponding colors. And then if someone calls this function, you can check if the category is inside of the names of this vector. So you could define a new variable called category is available to simply check if the argument is in the names of color map, and then you simply do an if else that checks if category is available. Then you return from the color map the thing that corresponds to category, and if not, then you return gray. Now if you re-execute this, you see now that you can work with vectorized versions of this, so you can stick vectors in there, but now you also see that you still get these initial names, and if you don't want that, you can simply pass this to the unnamed function, and then you only get the colors back. So that's a neat little pattern to avoid these if-else conditions. Simply store these things in a list, or in this case in a named vector, and look up things later. And the same thing works with functions as well. For example, if you take a look at the scales package, it has a whole bunch of functions that helps you to style numbers. For example, if I put in 1.2 into the percent function from the scales package, it returns a nicely formatted percent number. Similarly, I could take from the scales function or from the scales package the dollar function and stick in an amount of 1000, and then you'd see that I get nice dollar formatting. But now if you want to write a function called format number that depends on a number and a format specification, then you'd have to, or you could think of doing an if-else condition with this format, check if this thing is percent, let's do percent, and so on. But what you can also do is to simply create a list of formatters, which is a list, not a vector, but it can similarly be named, and then saying percent is supposed to be equal to scales percent. And for dollar, we want to have from the scales package the dollar function. And for, say, comma, we want to put in the scales comma function. And then if we know the format, we can simply get the corresponding function by the format name. And this will then be our formatting function. And then we simply apply it on the number that we have inside of our function. And now what I could do is to use this function with all kinds of different combinations. And if I do, we see that this causes an error. And the reason is because we need these double brackets here to get not a list of a single function, but just a single function. So that's why we need these double brackets here. And then if we do that, we see that this works out nicely. So this is another design pattern you can use to make your functions or your code more extendable. And with that, we've already covered a lot. So I'll leave you with that. Let me know in the comments if you like this content. Let me know in the comments if I missed something or went over something too quickly. Always happy to hear from you. Also, make sure to hit the like button if you haven't already. And now with all of that said, I say thank you for watching and I'll see you next time.